Kayda başladım. Şimdi şöyle, belki de artık İngilizce yapmakta fayda var. So far we talked about combinators, how they can handle compositionality, why their way of handling compositionality is an interesting take on compositionality because of having such a few primitives to do all kind of stuff. And now you talked about combinators being a bit too powerful in order to study the kind of things that we study in cognitive science. So we talked about selecting some of the few to do all that work. We know that S and K can do anything that is computable, but we also know that they are a bit too powerful, equivalent to a Turing machine. And then we got into one domain to study combinators named language. And we've seen that at least 3 combinators stand out in doing real kind of work, in trying to understand all and only human languages. We talked about B, we talked about A, and we talked about T. And next week we will start talking about other domains that I mentioned, namely psychology, language of thought, in philosophy of mind, and others. And so we'll be discussing more of the combinators in different settings and how they were chosen to do the task in the respective domains of cognitive science. What I have not talked about what I have not talked about so far is the topic of today's discussion. It's about uncertainty and the combinators. So I'm going to start sharing my slides with you, and the slides are available. Let me start sharing my screen. I have so many screens to share. I don't know which one is the one that I had in mind. Right, this one. Can you see it in full screen? Okay. So this PDF is called PCG for Probabilistic Categorical Grammar. It's in the repository. You can download and study it on your own. I'm not going to go over every single aspect of it, but at least I'll give you so the gist of how combinators can be put to work to study a grammar based on combinators under uncertainty. So let me start with the verb, and I've been, you know, that I've been emphasizing the verb ever since the beginning of class, mainly because it's the ultimate argument taker. It's the ultimate function that all languages share, and because of the way we categorize the syntactic and semantic structure of any word using combinatory categories, things that combine to give more and to give you the whole fragmented, where reference fragments the parts for analysis. We have seen that the verb really is determining the whole for the parts to take to unfold during analysis, and that's because mostly verbs are functions onto propositions, and that's one important lesson in history of linguistics, at least 20th century linguistics, that we learned, is that when things are, it pays to stay at the level of the clause rather than multiple clauses to study linguistic structure. And we learned a lot about the clausal structure by constraining ourselves to the structure of the clause. We looked at verb phrases, we looked at clauses, we looked at noun phrases. And we've seen that if you think of every syntactic function for any word as a function onto a proposition, or the noun phrases, that would be like a generalized quantifier. For verb phrases, it's the obvious generalization. If you have a predicate with one or many arguments, you take arguments one at a time, and in the end, you deliver a proposition, which can be true or false in a possible or imaginary world, realized or imaginary realized world. So it's important to study the verb to get into the real structure in language. And when you look at the verb, the form of the verb makes a difference in all languages. By that, I mean the root form, the stem form, that uninflected bare verb, so to speak, is the root form. Stem is something like the infinitive, like Turkish okumak, or English to run, and the finite inflected, for instance, ran, or John runs, or things like this. It appears to make a difference in reference, and that's a good point of start for studying uncertainty and how we can resolve uncertainty given a categorical grammar by training the grammar with real world examples to understand which category is the right for that kind of reference. So in 1a, you see that Mary would run is the grammatical expression in English. In Turkish, and Mary would to run or runs, in other words, the stem form or the finite form is not the right kind for would, the model in English. In Turkish, that would be like okuyabil, but not okumak bil. Okay. So in the first one, it's the root form. In the second one, B, Mary wants to run is the stem form, so to speak, and the finite form and the bare form is not the right kind of category for verbs like want. And in the last one, you need the finite one, Mary runs, and not run or to run. In other words, having a different form for the verb and having means that these are grammatical and ungrammatical in certain contexts, because would or want or run essentially are requesting different kinds of eventualities. and when your categories are constructed by reference, as we do, then we're essentially I'm checking the part whether someone joined in or not in the process. Basically, what we're saying, the implication of examples like one is that these are different categorizations of the word run. Like run, to run, and runs will be different, and that's going to make an effect in training, in training your categories based on the kind of referential properties that your exposed data manifests. So in A, the references to construction of possible words, like would take construction of possible words. In B, it's a reference to such constructed possible words. And in C, you're referring to an actual or imaginarily realized word. Okay, so in that sense, there are different kinds of references, and because of difference in reference, there'll be a difference in categorization. That's the idea. But it looks like the same verb. So if there are at least 3 different categories for the same verb, how am I going to train to make the difference in reference is a critical and important question. Okay. So I talked about this in class, so we can talk about it again. The category choice may reveal decision points, and I'll talk about what do I mean by decision points. So if you have a certain intended reference in mind, then you may be referring to different kind of category than the ordinary category of play. So when you say she played the piano for an hour, you're apparently referring to ordinary act of play, a single act of play, like in 3A. Same in B. She played the sonata for in an hour, meaning she played it. It's a completed event, and you did it in an hour. But if you look at the ungrammatical examples in A and B, she played the piano in an hour is a bit odd. She played the sonata for an hour is a bit odd, because when you play the sonata, you're playing a piece and it has a beginning and an end, and that kind of an adjunction is considered unusual. But when you change the reference of play to something else, like in C, a repeated performance, she played the sonata for a year is fine, because it's not like you played the single sonata in a single performance for a year. You performed the sonata, let's say, as a concert pianist for a year, so it's repeated performance. And in D, she played the piano in a year, meaning you master by practice. So I categorize this first as this. The first categorization may be very crude, like okay, there's a subject S under MP. This under MP is the subject, the performer. It performs a piece, and it has a duration. That's for C, or it could be like an instrument, like in 2D, and you play the instrument, you master the instrument in a certain period. Or as you practice more and more of these linguistic constructions, you may begin to see that these pieces and periods and instruments are essentially noun phrases and prepositional phrases. So you can generalize even more to extend the idea of reference for a noun phrase. So I can say this is a noun phrase for a score, meaning some kind of piece, sonata, or a fig, or whatever. Or a tool like guitar or piano or whatever. And what I mean by intent, the decision points are things like this X's and Y's as placeholders. So when they are for the iterated performance, this X means something. If they are for master by practice, this X stands for something else. And all of this is sort of disambiguated by the choice of reference. If you intend to use this category of play, then you're going to say, I'm expecting a decision points for X's and Y's and Z's such that one is for iteration, the other is for playing, and I do this repeat, and this is about practice of Z. And I use it for display, for D, this is for performance rather than practice. So Z is the performer, and this iteration is essentially over repeated performances of not the practice, but the performing event. Okay, and this is important because we are trying to explain the ungrammaticality of A and B, given the grammaticality of C and D, and we explain that by saying. That's one explanation, of course, there can be others. We're saying that that's because of shift of reference, therefore shift of category that allows you to do that. And when you choose the category, that gives you the decision points as placeholders for you to fill in, like the performer or practicer, a repeated performance of a piece, or repeated practice of an instrument and things like this. Okay. Now, all of this, of course, is again about the verbs, and you can think of this function like either this practice, either this perform, or whatever, as functions on the propositions. Why? Because they're all onto S. And if S as a syntactic category stands for a clause, you're basically saying I'm making a single proposition, maybe about an event that happened over time, many times. But what I'm saying is a single proposition. Okay. Now, when you look at this compositionality and how are we going to train these categories to understand this compositionality, several things will pop up. One is the thematic structure, sort of who does what to whom, and what are the roles, like agent, patient, beneficiary, things like this. There is the argument structure independent of the roles like X's and Y's here, and their structural differences because of asymmetry of structure. And there's going to be a difference in word order and tense and aspect and mood, because basically the argument that I made here is that having a tense aspect or mood, like in A, would make a difference in what category you're training at. Okay. Now, when you look at how these things are studied in linguistics, you're going to see a lot of differences. And here's a brief history of what's been done. One argument says that you can get thematic structure from argument structure. The other one says you can get argument structure from thematic structure. There's an argument basically says, well, syntax suffices to do all that. So you don't, in effect, saying that syntax suffices means what we write after the colon here is not necessary. It can be inferred from syntactic categories alone. Okay. So it is not writing categories, abstract categories as things means your grammar is a grammar of correspondences. And this idea goes back to traditional categorical grammar, beginning of 1900s. But if you take it all the way back, it goes back to Plato's correspondences of abstract ideas as real things in your mind and correspondence to the real world. So again, like many things in life, this goes also go back to Plato. And there's another brand that says, well, semantics suffices to all this. This is more like the cognitivism in cognitive science. Semantic structures can themselves take care of the limited nature of linguistic behavior. But what the categorical grammars are trying to promote is that it's actually the correspondence, and that correspondence is necessary because of examples like syntactic identity of semantic differences. Remember, I told you, mentioned control verbs like promise, persuade, expect, and want. And we've seen that although their syntactic structure, the surface structure, the phonological structure is almost identical, in fact, really identical, their semantics are different. Therefore, it's necessary in this way of thinking that they make a correspondence to understand the differences in syntactic identity. So that's the necessity argument. The sufficiency argument is essentially saying, well, composition is enough to give you all that, and you don't need more than that. And that's essentially the explanation of surface constituency. And of course, if you're going to have categories like this, then you're going to have to worry about how these categories are learned in the first place by a child and by any native speaker. And by learning, we mean, well, how do we get these syntactic forms and logical forms, the predicate argument structure, and phonological forms as we proceed at every step, so that in the end, your grammar is essentially a grammar of correspondences. So that's another way of saying, if you take the first four, like thematic structure from argument from thematic structure, syntax suffices, semantic suffices, they all imply some kind of interfaces and maybe independent computations. But what categorical grammar way of thinking basically says, well, although they may be interfaces, after all, semantics cannot be reduced. It cannot be reduced to syntax. Syntax cannot be reduced to just phonology. These interfaces might be quite trivial because the same computational process is doing all this. And that's the basis of the learning algorithms that I'm going to talk about. If these interfaces are pretty complex, then they must be learned independently, but that would not explain the limited time frame of language acquisition in children. You would have seen, we would have had to have seen much more variance in child language acquisition if these interfaces were not trivial. Now, what are these primes that we mentioned? I keep like practice, the meaning of practice, like practice prime, perform prime. What are these primes for? Well, there seems to be a universal conceptual space about things and actions and events. We just don't know what that space is, but there is a good deal of work on this. For instance, Leonard Talmy's work. The interesting thing about that space is it's quite structural. It's asymmetric. So there are many things, more actions that an agent can do to a patient, but patient cannot do to an agent, and things like this. There's this asymmetry of things. And since any language is learnable in any place, given sufficient exposure at the right time in the developmental stage, all of these languages, human languages, must be homomorphic. That is, some kind of similarly structured in that space, because any language is capable of being your native language. And since languages differ in surface structure, that surface structure cannot be really homomorphic to that space, right? So we want to understand, although there is this structural similarity, as we have seen in the control verb, it can't be the whole story. Okay, and that sort of brings us to categorizing word order along with syntactic and semantic structure, and that's how we got to the combinatory categories. And there is a very sort of insightful remark by a psycholinguist, Merrill Garrett. He said that the first thing to note about parsing or analysis in language by native speaker, not by the analyst like the philosopher or the linguist, but by the native speaker, is that parsing is a reflex, and that needs to be understood. And whether it's a reflex, I mean, just think about this question. Try to turn off your parser. If it were in the reflex, if it was something voluntary, you would be able to do that. But just when you think, you just turn off your parser and you're not really interpreting anything that's been said to you, or you're not thinking of saying anything. I can say something so ineffable that you see that actually your parser hasn't really been turned off. You've been listening. It's just that it's a little difficult to turn these things off. It's almost like involuntary in that sense. Even in your sleep, if something striking happens linguistically speaking, you respond. Well, how can you respond if your parser has been turned off? So the asymmetry of structure, we talked about it in great deal, so I'm not going to dwell on it too much. Mary liking John is different than John liking Mary, so these have to be represented differently. So again, the problem I'm trying to get at is I'm going to represent difference in such a way that they are trainable. Okay, so I'm trying to represent differently so that I can represent their structural and referential differences. And then I'm going to train on that to see which category is favored under what circumstances. Okay, and you can see these differences in interpretation from examples like 4. When you say the window broke, it's not like the window is an agent. It is something happens to the window and it becomes broken. Okay, so somebody breaks the window in A. Actually, it's just that this is a different categorization than for B. The stone broke the window. Now, my stone can cause a window to break, of course, but that doesn't make the stone an agent, because stones don't do anything by themselves. So even B is different than C. The man broke the window with a stone. It's different than B and A and B. Here, there is an agent, the causer, that causes the window to break, and he does it with a stone. So all of these are different categorizations, and we're trying to show the difference by having different kinds of things, placeholders for reference to resolve. Okay. So you might be thinking, well, what are these primes and predicate argument structures, or sometimes it's called a logical form, sometimes it's called a predicate argument structure. predicate argument. My preference is to call it predicate argument structure, but it's too long, so sometimes I just call it LF. But there are differences, but I'm going to skip that. So these you can think of as things that arise from your conceptual space, either derived or primitives, but we don't know what they are. They're just placeholders for the concepts that we are familiar with from exposure. Okay. Now, when you look at surface structure, the surface structure, by the way, is a term that Chomsky introduced in the 70s. Basically, it says, well, when you make an analysis as a native speaker, you're fragmenting the expression by using its categories. That creates a structure in the surface. So it's not just a phonological structure. You're fragmenting the analysis is the surface structure itself, and that needs to be understood. It's not just an empirical thing. It's assumed to be constructed by the native speaker and the hearer. The syntactic part of the surface structure is captured in categorical grammars using syntactic category. And when you look at promise, persuade, expect, they're identical because their surface structure is identical. When you look at broke, you're going to see differences in the example. Some are agentive, some are not, but without the predicate argument structure, it's difficult to tell. And I'm showing you examples from other languages like Welsh, Tagalog, and Turkish and Portuguese to show you that the differences in word order is so much that all kinds of directionality has been attested in all languages. For instance, in English, complement clauses, the arguments that are themselves sentences are to the left of to the right of the verb. In Turkish, it's to the left, as you can see from here. Ben kitabı okumayı savundum. Kitabı okumayı is before the verb. Okay, so all kinds of word orders have been attested. But the story of the categorigram is that these syntactic categories are half the story. Okay, because of things like this. How can I distinguish a S under MP kind of broke from a transitive broke? And transitive broke, I could have said the man broke the window without saying with a stone, not taking the stone as an argument or instrument. Then how can I distinguish agenthood in B and C is not addressed yet. So this is the critical question. If the surface structure is not universal, it's not homomorphic to a universal conceptual structure, whatever that means, whatever that is, then how in the world do children learn the word of their language? Okay. Well, one idea is to have to assume a linguistic structure like this. There is the form and the meaning, the model word, so to speak, and these correspondences are correspondences of these what you perceive, and what you think, what you perceive means, and you create a list of correspondences like this. And the whole idea is to train a grammar like this to understand its reference and decision, essentially. Now, in this idea of learning, syntax is a hidden variable for the child because no one tells the child what the syntactic structure is. It has to be inferred. Okay. The meaning part, you may say, well, I think when someone says X, the child understands X prime, whatever, and you can make assumptions about semantics, but essentially the idea is in this picture, the child is exposed to words and forms and syntax, sentences, and you think this means in that world something, okay? So nobody says anything about what the syntax is. That thing has to be inferred. And that's going to set up what is called a mental grammar sometimes, a grammar as a psychological object. But because of the uncertainty in the world and possibility of interpretation, these grammars are necessarily probabilistic in the sense that the grammar is just your ordinary. What that means is that your grammar sits in a probabilistic space, but the grammars in that probabilistic space themselves are just your ordinary grammars. The category is specific. So when you say a grammar is probabilistic, we don't mean this S is unknown, this MP is unknown. It just means that whatever that grammar is, it sits in the probabilistic space of possible grammars. Okay. And here I made a connection to next week's talk, discussion. If you change this in nature of categories from linguistic categories to, for instance, action categories, you're going to end up with what's called in AI planning and scripting. And we're going to talk about that next week, I think. So what we really have is actually the syntactic type, the category like this, and some kind of understanding of what that syntactic type means. So for instance, for broke, take D. This is a broke where there's an agent, and the agent does something with an instrument. This one is again a causative break without an instrument, but that one is not. This means something breaks, but it's not the cause of breaking. Okay. And I mentioned this because when you look at word orders, if you take the transitive, subject, verb, and object, there will be 6 different variations of that, right? SVO, OVS, SOV, OSV, VOS, and VSO. But in categorical way of thinking, there are 2 more alternatives. One I called SVO prime and also OVS prime. Why? Because SVO, why is it this one SVO? Because remember, this is the category of the verb. Right? This entire thing is the category of the verb. This noun phrase corresponds to X, and look at where X is. It's the patient, structurally speaking. So that means the thing to the right of the verb is an object. That's why it's SVO. And without the logical form, you cannot say that. Just because you have S under MP over MP, that doesn't mean SVO. But given that, it becomes SVO. Okay. What is subject? What is object? Now can be written more explicit, and that's the benefit of having a correspondence of semantic placeholders and syntactic placeholders. But since this is possible, it's also possible that I can get this all as the last thing. First, I can get the subject. Remember, look, this under MP is this X corresponds to X, but this X is now the subject. So this is S. I can get S first and then O. This is also SVO. And in the beginning, this is categorically possible. Although in phrase structure grammars, people say when you have a transitive, there are only 6 variations. In categorical thinking, there are 8 variations. Similarly, if you take OVS, there are 2 ways to get OVS. This is one way. This is the other way. Get the subject first. Why? Because this MP corresponds to X, and this X is now on the outside. Okay. So there are 2 more variants in addition to 6, and that's only possible for verb medial languages. There are no other possibilities for SOV, right? This is the only way to get SOV. But this is not the only way to get SVO. And since all of these are in the beginning equally likely for the child, how do I know that this is the right one for English? This could be the right category for English. It all depends on the data and how you interpret the data. So what we're going to do in the learning scenario is we're going to assume the child starts with all of these possibilities. And because of exposure to the English kind of data, some of these categories will have more weights in them because they are more likely given the training data. Some will be less likely. And if you keep doing that, what's going to happen is some of the categories will be so prominent in terms of their belief, the child's belief in them, that the others will be almost negligible because of training. Okay, so basically we're going to assume that the child starts with any possible word order, and by being exposed to different kinds of data, it's going to favor certain categories and not the others. Okay, and these possibilities are all possible, all attested. So I mentioned 8 possibilities. Here are the languages for them. Okay, so we think that Perry is the language in B is OVS prime. There are good reasons to believe that in Perry the subject combines first with the verb. I'm not going to go into linguistic details, but that seems to be the most sort of reasonable interpretation. So all of these are possible. In other words, and since we don't know whether the child will be exposed to English, Faztek, Ishkariana, or others, they must be all available in the beginning and picked up by language by having a certain kind of structure in the child-directed speech. Okay. So again, here's a sort of thought experiment that you can do with the tool that I mentioned last week. Just consider the syntax as a hidden variable. In other words, I'm going to learn these categories by positing all of them, and adjusting their weights. And the way it's learned is by trying to parse the input data to find the likelihood of these categories given the input data. Okay, so we're going to assume we start with a universal combinatorics like B and A and T, and since that's invariant, what is variant is your categorization of what you're being exposed to as a native language. And you can do this experiment in the bench, and you've done it in the midterm and the homework as well. So without getting into too much detail, but showing you how the underlying machinery works, let me give you this. But I realize that I've been talking for about 45 minutes now. Is this a good time to take a break, or I can? From now on, I'm going to cover a bit of how this probabilistic inference works. Shall we take a 10-minute break?
Bana fark etmiyor hocam arkadaşlar.
Okay, let me finish this then, and then I'll probably go for. Okay, so what's going to do is L is just for logical form, S is for a sentence, and D is derivation. By derivation, I mean that's all that structure that we did, like John promised Mary to study and things like that. Derivation is the set of steps that you need to follow to set up the analysis of the expression itself. That's called derivation in this slide. So the hidden variable problem basically says, well, what is the most likely logical form given your weights, vector of weights, that is your beliefs in your categories, and given a clause onto S. This is turned into this, but since I don't have direct access to how we obtained the S, I need to go through all derivations and say, well, this derivation gives of this derivation of S gives you this logical form. Another derivation of S gives another logical form, and from that I find the most likely one. Argmax means get the most likely L given S and your current beliefs. So I'm going to turn this thing. The reason why it's called hidden variable problem is I turn this problem, what is the most likely logical form given the clauses, by saying, look at all the derivations and pick the ones that give you L and pick the L that gives you the max, given these things. So it's hidden in the sense that these derivations are inferred, not observed. So you have to make the transition from observed data into a sequence of derivations from which you can pick up the logical forms and say whether it's the one that meets the understanding that is assumed on part of the child. Okay, so these things, by the way, these data are essentially beliefs, and they're not probabilities. The way you can do probabilities is if you just use the very simple frequentist approach, you can look at all sentences derived, all through derivation, particular derivation for a particular logical form, and you sum it up over all logical forms and derivations. It gives you a ratio of a frequency of certain logical forms, and then you can think of these weights as probabilities. That's why here I cite probability of L and D, although this is itself and not a probability, it's just a weight. So P here is a number between 0 and 1, whereas these theta prime, a vector of weights, can be anything. It doesn't have to be between 0 and 1. So what is this F? It's some kind of measure function, like how many times have you used it? Which primes have you used, like practice prime or real prime, whatever. Some kind of local measure of counts of things that you've seen. Okay. So what you do is given the exposed data, you're going to update the weights so that you basically updating the weights means based on the current data I receive, I'm revising my theory about what English I'm being exposed to, and that I did on the basis of what I'm exposed to alone. Okay. So what does it mean? Well, when you look at the training set, look, syntax is a hidden variable. You might be hearing about true dog mommy, meaning this is a real example, by the way, from Eve. So like, I mean, that means mommy throws does something funny with the dog, or things like this. And look, I have the surface expression, and I have an idea about what that surface expression might mean, but I don't know what kind of syntax does it. That's something I learned. Okay. So if you go through the training, basically initially you have your weights all equal in the beginning, and then after training they're going to have different kinds of weights depending on your language being exposed to, and that's the whole idea of making a category more likely for English than, let's say, Turkish. Okay, if you're exposed to English, you're going to have SVO more likely. If you're exposed to Turkish, you will have SOV more likely. So that's the idea. Okay. Maybe this is so we need to look at training set. The training set again consists of expressions and their meanings, at least what they think it means. Okay, something like this here. Mommy ate the biscuit means mommy is the agent and she eats a definite biscuit, whatever. Okay. So your adjusted weights are essentially your weights about giving a certain logical form. And this logical form and syntax connection is given to you by going over all derivations of the same logical form for the same category. So we're turning it into a hidden variable problem ourselves by saying, I'm going to look at all the derivations of things like these. And since different derivations will use different categories, I'm going to get an estimate of the likelihood of the categories given the current exposure. Okay? And if you take, so basically, this is the model of structure prediction. So this is like, what is it? The likelihood of the vector space. And if you take the derivative of this, change in inverse, change of parameters, it's going to be expected value of this versus expected value of that. I'm not going to go into details, but I'm just trying to show you that these expected values can be computed from derivations themselves. So you can get an estimate of how the parameters change. This is a partial differential of likelihood of new categories given the change in the parameters. Okay, it roughly corresponds to the difference between item J's contribution to correct parsers versus contribution to all parsers. If that's positive, then that category is used more and more in the derivations. If it's 0, that means that category is making no difference. If it is negative, that means it contributes less to correct parsers and more to others. Therefore, it's not really improving given the current data, exposed data. Okay. And then you apply, since this is a very complex function, it's difficult to get the closed form. So this is what we're trying to get, a partial derivative of the expectation. And since this is a very complex function, you just do stochastic gradient. I mean, there are thousands of ways to do this. So you begin to approximate this using these, and you get a look. In the end, at every step, you're adjusting the weight vector. It's the previous vector followed by this thing that training does to you, and that's essentially likelihood of the logical form given the current weights. And these things are learning parameters like learning rate and learning rate. How many times do I iterate? How big is my step at every gradient and that kind of stuff. I'm skipping all that stuff because it's at this point, it's a technical detail. So basically, if you do this, then all possibilities for all verbs are entered in initial mental grammar. So I mean, remember, in this way of thinking, if you're going to expose, say, well, why is it that in English certain categories are prominent and in Turkish the others? Well, in the beginning, they all have to be equally likely and then biased based on data. Okay, that doesn't mean that this child starts tabula rasa, by the way. It means because you have to create the initial semantic space in the first place, and that's for the theory of grammar to do. Why? Remember, he said, these are the probabilities. But how do I know that? Well, that's the theory. That's coming from theory of grammar. These are the possibilities. Have them in the beginning, and their weights will be adjusted based on exposure. So this is not a hardcore empiricist tabula rasa kind of training. Your theory of grammar basically gives you category space, and you train on that to get English, Turkish, whatever. Okay. I mentioned this because sometimes this probabilistic way of training says, well, oh, you're just doing probabilities and statistics. That's not the theory of grammar. But it is. What sets up the category space in the first place is the theory of grammar. Okay. So what do? You assume a mental grammar, and then you assume a certain set to be true. In other words, what the child is exposed to, and you assume that they are understood in certain ways. You may be wrong, but you have to second guess the child as an analyst. That's what the child, but that's what the child thinks it means, kind of thing. And then you assume a certain form meaning correspondence, and then you parse to learn to re-estimate the parameters. Okay. So when you do that with that kind of data, this is what you get. And I mentioned that. I'm just showing it again so that you can see what it looks like in the beginning. All the weights are same, and all possibilities are listed. After training, some are more. For instance, this has more weight. This and this has more weight, and these are now negative. Apparently, they contributed less to correct parses than to incorrect parses. So they're believed less. And you do that, and I'm so the training set is something like this. Again, no syntax. So expression, meaning. That's what we think the child thinks it means, kind of thing. And then, and the mommy means mommy prime, and you can put primes if you like. Sometimes I do that, sometimes I do. It's just that after the colon, this is the sort of predicate argument structure of what we think the child understood from this. Okay? So if you do this experiment with the English data that I showed you here, this is the experiment that we ran, and this is what you get in the belief of categories. SVO and SVO, initially they're all the same. The blue, they're all the weights are the same. But after the training, SVO and SVO prime is much more prominent than the others. Just from this data, you can say, well, the child is beginning to get the word order of English and the structure underlying that word order. What is subject, what is object, and that kind of thing. Okay? So it's just 3 verbs and 8 categories for all verbs. And this is what you get from this mini thought experiment. And here are the verbs themselves. This is 8, because I had 8 many times. I have true, I have saw. So let's look at the verbs individually. This is 8. As you can see, SVO, and the first 2 columns are SVO in this notation, and the others are OVS, OVS prime, whatever. You see that 8 is making a big difference in SVO prime and SVO. Here is true, same thing, except that, apparently things have gone worse for true. Look at 8. For what is the 4th column? OVS prime. So if you look at OVS prime for true, apparently true is worse than 8 in terms of OVS prime. Since this is a made-up example, I didn't go and check in why that is the case, but we have a real data for Eve, one of the children that studied extensively in psycholinguistics, and you can see why extensive use of for instance, true might throw the child in different directions about what throw really means. And this is so. It's consistently, in all 3 verbs, SVO and SVO prime are prominent, and the others are less and less prominent. Apparently, so didn't make much of a difference in the others. They're equally worse, so to speak. True is not like that. It's worse in these categories and not in the others. And 8 is even different than the 2. And they are worse. It's worse in these categories and not too bad in these 2 categories. At least its weight is not getting worse. Okay. So from this, you can say, well, look at these classes of verbs clustering around SVO and SVO prime. And you can say, well, that's because you're being exposed to an SVO language by the mother, and that's why you're getting it. Okay. So what's the point of this, and how is that relevant to the combinators? You can think of this as somewhat realistic environment for the child, because I'm not assuming on behalf of the child that they know what the syntactic category of that means. Nobody tells them that the dog ate the biscuit is an S. that has to be figured out by derivation, by simulating the derivations on behalf of the theory of grammar to say, well, if it's an S, that the likelihood of this logical form is a certain value, whatever. Okay.
Can I ask something?
Sure.
What is the purpose of the sentences in the training set? The dog walked, something like that. Walk and sleep verbs.
Well, that's what we're exposed to. These are assumptions. If this is the data the child is exposed, this is child-directed speech. And we're trying to figure out what kind of grammar might be materializing in the child's mind if she's exposed to that kind of data. So we just assume the dog, someone says the dog walked, and the child understood there's a definite dog and it walked. This is a made-up example. I can show you maybe next week some real-life examples from Eve, which is in the database as well. It's a private database because you borrowed it from someone else, but I can show it to you in class. But if this is the data, if this is the real thing, then it's going to give you biases in categories. That's the idea. So it's not a psycholinguistically valid example. It's just a way of showing how categories can cluster just by looking at data. So this if you look at the hidden variable problem, it's pretty complex problem. Here's the hidden variable problem. Right? I am turning the likelihood of this logical form given the sentences by looking at all the derivations of this logical form. So this summation is the hidden variable solution problem. And since there will be so many different variations, I'm sure you found that out in your midterm that there can be 18, 15, whatever, given an expression. There'll be so many of them that this is really a complex problem. But if your theory is computationally efficient enough, you can attack this problem. And categorical grammar is one of those theories. And we have to explain the computational efficiency of this thing, if computation is underlying all this work at all, because we know that the child can do this in a limited time frame. So it's not like in one language you learn because of the complexity of word order or whatever, you learn it at the age of 4, and in the other language you learn it at the age of 1. That's not what seems to be happening. There's a limited time frame across cultures, across educational levels. So something must be doing something. The complexity of the grammar should not lead to differential in computational efficiency of the solution of this problem. Otherwise, we won't be able to explain how the child converges in a limited time frame. So how that relates to combinators is basically, first of all, having a correspondence is a prerequisite in this. I mean, if you're going to train it, and if you're going to treat syntax as a hidden variable, it is necessary that you have a correspondence. And Combinators' way of handling that correspondence gives you a very sort of simple building blocks to tackle this problem. Instead of saying, yes, this correspondence, but this correspondence can be, your first order logic of very general mechanism. So you should try anything. But basically, the combinators are saying, well, this is compositional structure, and that can arise from very few combinators, which are very efficient to compute. And this will be the sufficiency argument. Okay. So that's the gist of the argument, and that's how. This is one way of putting sort of categorical complex categories to work in understanding the role of combinators in, for instance, in understanding child acquisition. language acquisition of the children. Okay. So maybe there could be questions, but maybe I should stop recording and